under extraction of metals, we have actually looked at iron, if you still remember. We have looked at zinc, if you still remember. The only ones that are remaining are aluminium and copper. And yes, aluminium, copper. And these two are extracted by the same process. Copper is extracted by thermal decomposition, then purified by electrolysis. Though copper has many methods. There is copper smelting, froth flotation, as well as thermal decomposition. So we're going to look at those forms. And then among the most reactive metals, we have aluminium, zinc, or we have aluminium, calcium, potassium, sodium. Those that are extracted by the method which is electrolysis. So today, I actually want us to look at electrolysis. Then tomorrow we're going to look at physics, because Mr. Matongo is preparing the paper. Then the other day we'll look at math. We have to strike a balance. So the notes are projected up here, but I will also have a word to add in as much I will also engage you in one way or the other. So today, we are looking at extraction of aluminium. So, according to the few discussions we've had, what method do we use to extract aluminium among other most reactive elements?
We use
because we only have
composition.
We only have electrolysis, reduction by carbon, as well as thermal decomposition. Which one do we use to extract more reactive or reactive metals?
More reactive metals. I'm thinking reduction by carbon.
No. So this is the order, even on the reactivity series. The most reactive metals, electrolysis, relatively reactive metals, reduction by carbon, and the least reactive metals, we extract them by thermal decomposition.
Okay.
Now, the information is up there saying aluminium is extracted from a metal ore. Remember, each and every metal that we have, for as long as it does not occur naturally in nature, it should have the metal ore from which it is extracted. Just like iron has got many metal ores, but the chief metal ore is hematite. Zinc also has a lot of metal ores, but the chief metal ore for zinc is zinc blende. And
Okay.
aluminium also has many metal ores, but the chief metal ore from which it is extracted is called the bauxite. So you don't have to forget. So
Okay.
the common name for the metal ore, this question might come in an exam, it might come in the test, is actually called metal ore. For the metal ore for aluminium is actually called bauxite. Bauxite. Now, from the name bauxite, it is very difficult to know the chemical composition. It is very difficult to know the chemical composition. The only way we can know the chemical composition is by understanding the chemical name. So the chemical name for this bauxite is actually zinc, is actually called aluminium oxide. So the chemical name for bauxite is actually called aluminium oxide. Now, it is from this aluminium oxide that we are able to tell the chemical formula. It is from this chemical formula that we will be able to tell the chemical formula. So the chemical formula for bauxite, whose chemical name is aluminium oxide, aluminium we understand, it's Al, has a valence of 2. Then oxygen, it's O, has a valence of 2. Aluminium 3, oxygen 2. So when these valences are interchanged, the 2 on oxygen is written as a subscript on aluminium. The 3 on aluminium is written as a subscript on oxygen. That is how we are able to write this chemical formula. Any questions so far? Okay.
So far, so.
And we were saying that more reactive elements form very stable compounds. So at this aluminium, we expect to have a very stable compound. That's why the method we're actually using is electrolysis. So this point says here, aluminium is extracted by the method called electrolysis. So we cannot understand the electrolysis if we cannot understand the extraction if we don't know what electrolysis is all about. Now, just like iron and zinc, which is extracted in a blast furnace, aluminium is extracted in the electrolytic cell, which is called Hoare-Harrott cell. Hoare-Harrott cell. Now, in this Hoare-Harrott cell, we need to understand what actually happens. Electricity is involved, and heating is also involved at the same time. Now, what is electrolysis? Electrolysis, the point is defined here. Electrolysis is the process by which aqueous compounds form ions by the use of heat and electricity. So meaning during electrolysis, during the extraction of aluminium, this aluminium, first of all, must be dissolved. Why are we dissolving it? So that we form an aqueous compound. Now, when it is dissolved, we expect electricity to pass through. As electricity is passing through, we expect this compound to be heated. During that reaction, that is when we expect this aluminium oxide to dissolve into separate ions. Are we okay? Now, so we need to understand. Now, that solution, which is allowing electricity to pass through,
Yes, sir.
The solution that is allowing electricity to pass through, and at the end of it, it decomposes into formation of ions. That compound is what we actually call an electrolyte. So when you get aluminium, we dissolve it. Now, we don't just dissolve in any solution. I'll show you the specific solution that we use. You dissolve it. Now, because electricity is able to pass through it, and during that process, this compound decomposes, therefore, this solution is what we are actually calling an electrolyte. So an electrolyte is an aqueous solution that conducts electricity, or that allows electricity to pass through it, and at the end of the day, it decomposes, it forms the ions. So that's one thing you need to understand. So during the electrolysis, when electricity passes through this dissolved aluminium oxide, it's going to conduct electricity, and at the end of the day, it is going to get decomposed, or it's going to separate into different ions. Now, what really happens? So we are saying, because aluminium has a very high melting point, it is very reactive. That's why it forms a very stable compound with a high melting point. Remember, when two substances join together strongly, for you to separate them, you actually need a lot of heat. And that heat is coming from electricity. So to minimize the expense on electricity, we make sure that its melting point is lowered.
Okay.
So because aluminum oxide forms a very stable compound, which does not fully decompose on heating, when we are decomposing it by the method of electrolysis, we make sure that we lower its melting point by dissolving it in a compound called cryolite. So actually cryolite is another metal ore for aluminium, and we can clearly see that aluminium is present. So cryolite is sodium aluminium fluoride. So the reason as to why we do this is to make sure that the melting point of sodium oxide or bauxite is lowered, so that we minimize on the cost. So first thing first, you need to understand the method that is used. Secondly, you need to understand the metal ore. You need to understand its chemical formula. You also need to understand the reason why the first thing that we do is this aluminium must be dissolved in cryolite, so that we lower the melting point. Now, once this is done, then we are gonna get, after we've dissolved it,
Yes.
after I've dissolved it, then we're gonna get that solution and put it in the cell that we are actually calling a Hoare cell. Hoare cell. Now, what does it look like? First of all, let's look at this Hoare cell. What does it look like? So Hoare cell looks like this. This is our Hoare cell. This is what it looks like. So this cell here that we actually have, we can see that it's a cell. Now, because we are using electricity, we need to make sure that we understand the terminals. Remember, electricity flows in the conductor, and then we need to know the terminals, which one is a positive and which one is a negative. So the three major parts of this cell that you need to understand. One, the terminals. These terminals are also called electrodes. You need to understand the terminals. You need to understand the electrodes. How many terminals do we have? There are only two, the positive and the negative. So the positive is actually called the anode, which is a positive. And we also have the negative, which is called the cathode. The cathode is the negative terminal. So this is what we have here. We have the anode. Now the anode is on top. These electrodes are just dipped inside of a cell. It's like the way we do at times when we are warming water. Like at times where we do when we are warming water, we get our heating elements, and then we dip inside of water. So this is what we actually have. So the ones that are dipped inside, these are positive charged electrodes, or these are positive terminals. And then the other thing that we have is a negative terminal. The negative terminal is just the lining of this whole cell inside. The cell inside here, that is where we have the negative terminal. Now this negative terminal, both the negative and the positive are actually made out of graphite. Graphite is just carbon. So we've got the carbon positive, we also have carbon negative. These are terminals where electricity is supplied through, or where electricity is connected to this cell. And then remember, we're saying that the temperature here goes as high as 500 degrees Celsius. So this thing where we are carrying out this experiment, it must be very thick, and it is made out of steel. So this is the steel tank. So the walls around it is made out of steel, and it is actually called steel tank. So now when we get our aluminium, we dissolve it in cryolite, then we're gonna pour it in this chamber. So this is a combination of aluminium as well as cryolite. This is what we have. So we have aluminium here as well as cryolite. And this is what they have said. The aluminium dissolved, the molten aluminium as well as the cryolite combined in this cell. Any question? Any question? No questions? No question? Okay, now, so what follows is this. When this aluminium is dissolved in cryolite and is fed inside of the cell, we are saying that this aluminium decomposes. It ionizes. Yes. Distinct ions are formed. This is a point over here. That during the process, when we dip everything in here, this aluminium, the molten aluminium oxide, I forgot oxide, the molten aluminium oxide decomposes it separates itself into different ions. Which ions are these? We can clearly see that our bauxite is aluminium, 2 atoms, and oxygen, 3 atoms. This is our compound. So this compound that we actually have, during ionization, when it is dissociating, when it is decomposing, it is separating into aluminium alone as well as the oxygen ions. So this is what is being referred to in this chemical equation. That during this process, aluminium oxide decomposes into ions of aluminium as well as ions of oxygen, which are oxides. So this is what we have. We have seen aluminium here. There are 2 atoms. That's why we have a 2 here. And each aluminium atom forms a charge of 3 because it is in group 3. That's why we have that. It is not a solid. These are in the solution. That's why we're indicating aqueous, aqueous, aqueous. Not only that, oxygen also, there are 3 atoms. That's why we have a 3 here. And each atom has the charge of 2 minus. So this is what we actually have. Now, once this ionization is done, what we will have in the solution, we will have these ions of aluminium. We're also gonna have these ions of oxygen present inside of this solution. So what is going to happen is that because these ions have different charges and the terminals also have different charges, we expect opposite charges to attract. So we can see that this is our graphite anode, which is positively charged. So we expect the oxygen, which is negatively charged, to be attracted. So we're gonna have a lot of oxygen, oxygen ions all around. We're gonna have all these around the anode. Why? Because the anode is positively charged and the oxygen ions are negatively charged. They will actually be attracted. So meaning within the anode, there will be some form of chemical reactions that will happen when these ions attract. What else? This cathode, all around it is negatively charged, all around it it's negatively charged. So we expect this aluminium to be attracted to the lining of the cell. All around it, we're gonna have aluminium, or around it, we're gonna have aluminium attracted. So that is what actually happens. After these distinct ions are formed, then they are in the solution, they will be attracted to opposite electrodes. Aluminium, which is positively charged, will be attracted to the negatively charged, and oxygen, which is positive, oxygen, which is negatively charged, will be attracted to the positive terminal, as I've indicated. Then, from here, now what we're gonna do is that we're gonna see what really happens at each electrode. Remember, the positive terminal is the anode, the negative terminal is cathode. What happens on those cathodes? On those electrodes. So down here, we are saying what really happens at the cathode, which is a negatively charged chemical species. Which one do you think would be attracted to the negative? Which one do you think would be attracted to the negative? Is it the oxygen, the oxide, which is negatively charged, or the aluminium, which is positively charged?
I think the oxide which is positively charged.
Oxygen is negatively charged. Look here. Look here. Oxygen is negatively charged. And aluminium is positively charged. So which one do you think would be attracted
Oh
to
yes, okay.
which is negatively charged?
I think
Which
it's
one?
the aluminium which is positively charged.
So this point says aluminium is positively charged, and hence it gets attracted to the negative electrode, which is the cathode. Now, first of all, you need to understand that for it to gain the positive charge, for it to become positively charged, it means the aluminium lost electrons. So now when it gets attracted to the positive terminal, that positive terminal is actually in need of electrons. Oh, it has a lot of electrons around it. That's why it's negatively charged. Now, aluminium at that point is already positively charged, has already lost electrons in the outermost shell. It can no longer lose more. So the only thing that it does, it gains those three that it lost at the beginning. This is what we are showing here. So when aluminium ion gains 3 electrons, it behaves as it was at the beginning. It becomes a real metal. Now remember, this metal is within the solution. So what do we expect it? We expect it to sit at the bottom of the cell. You get the point? So the ones that are sitting at the bottom there are not aluminium ions, but aluminium metals after gaining electrons from a negatively charged electrode, which is the cathode. So in case they ask, explain what happens at the cathode. Just say at the cathode, which is a negatively charged electrode, aluminium ions, which are positively charged, are attracted to the cathode. They gain electrons, they become full metals, and they are actually deposited at the bottom. Then we are done with the aluminium. Let's see what happens now at the anode, which is on top, which is a positive charged electrode. So we are saying that because the aluminium is because the anode is positively charged, and these ions of oxygen are negatively charged, we also expect them to be attracted. Remember, the oxide ions are lighter, so as they tend to float going up of the solution, that's where these electrodes are. So these oxide ions that are negatively charged are actually attracted to the positively charged electrode. Now, because they are negatively charged, meaning they have a lot of electrons, the ones they gain from aluminium. So at this point, these anode electrodes are in need of electrons. Therefore, they are going to donate the electrons to the anode. Now, remember, this anode is just the carbon. So when this carbon actually reacts with oxygen, what is formed is carbon dioxide. So each time this reaction happens, carbon dioxide is produced and it is bubbled off the cell. Now remember, the carbon part is coming from the graphite. The carbon part is coming from the graphite. So what we actually expect is that every now and then, the size of this anode gets reduced. Because each time carbon dioxide is formed, the carbon part of this gas here, the carbon part is coming from the graphite. A good example I'll give you is when you are cooking. When you are cooking, you've cooked in shima. Now, when you are cleaning the cooking stick, if you are very rough, the remains part of nshima comes out of the cooking stick together with parts of the cooking stick. As you do the cooking every now and then, you realize that the size of the cooking stick has actually reduced. Then mom will say, we need to buy another one. So this exactly happens. As this carbon dioxide is formed, the carbon part is coming from the graphite anode. It gets reduced, it gets reduced, it gets reduced. We'll reach a point where the size that will remain is quite small, that cannot do its intended purpose. As a result, we will have to replace the anode with a new one. And that is the point we actually we have. As this happens, the size of the anode keeps on reducing, hence we need to frequently be replacing with the new ones. So that's what happens. Once this process is done, then we're gonna run our aluminium off the chamber. So that's why this cell says that the exiting point for aluminium is actually this point. Because aluminium is heavy, so we're gonna get it out of this chamber right from the bottom. And this aluminium will actually be collected in a molten form. Even in as much as we said it is a solid, but it is in a molten state. It's not completely a solid thing that we obtain. We obtain it in a molten state. It's a metal, but not as strong as it was. It is actually in a molten state. And now we also need to understand that this aluminium that we have extracted, where do we take it? We look at where we can use it. Because aluminium is very useful based on the prominent properties that it actually has. So in the few minutes remaining, one of which we are saying aluminium is a good conductor of electricity, therefore it is used in making overhead electrical cables. Overhead electrical cables, we use aluminium. Because aluminium also is a good conductor of heat, we can actually use aluminium in making of kitchen utensils, cooking utensils. I'm sure it's now that we are slowly diverting, but back then there were those old pans. Those old pans, they were actually using aluminium, especially when you go for ZAF training. The pan back then that they were giving are made of aluminium because they are light. When you buy butter, Blue Band butter, you remove the wrapper from the top. You find that wrapper which seals aluminium, which seals butter, is actually made of aluminium because it's resistant to corrosion and it is non-toxic. It's not poisonous.
Yeah.
Even Rikoff, most of tinned food, they use aluminium because it's non-toxic and it's not corrosive. It's resistant to corrosion. Planes some parts of the planes are actually made out of aluminium because of low density. They are very light. If we were to, and also cheaper to find, if we were to use very heavy metals in making of planes, yeah, it can take off, but with difficulty. So we need to make sure that we use something of low density. Also used for making iron sheets, making alloys, also making paints, among other uses of aluminium. So that's how we extract aluminium. Can I have questions?
So far, I don't really think I have questions.
You should have one or two.
Okay, one or two. On the Okay, I didn't really understand the process of how molten aluminium decomposes.
You don't